Hello students, in this video we will discuss about linear transformation. Linear transformation means we are taking one mapping or a function from one vector space V to another vector space W. From V to W, then it satisfies two conditions where when you are taking one vector U from V, then transformation of U that is belongs to W. Then it satisfies two conditions, that is transformation of u plus v equal to t of u plus t of v for all uv belongs to first vector space, and t of cu equal to c into t of u. It is nothing but vector addition and scalar multiplication in terms of transformation. So a mapping is said to be a linear transformation if it satisfies these two conditions. Now the set of all vectors in u in V such that t of u equal to 0 cap or 0 tau is called kernel or null space of a linear transformation. That means kernel T means when you are taking any vectors from V. Suppose this is vector V, vector space V, vector space W, and this is a linear transformation from V to W. Suppose you are taking u here, then this image should be 0 bar. Transformation of u must be 0 bar. Then this u is belongs to kernel T. Suppose I am taking here V, it is whose image is not is 0 bar. It is T of V. Suppose, of course, V is in first set, but V does not belongs to kernel T because whose image is not 0 bar. If u image is 0 bar, that's why this u is belongs to kernel P. So kernel T definition is what? U belongs to first vector space such that whose image is 0 cap or 0 bar. 0 cap, why we are using in the sense 0 bar, when you are taking a 0 vector which is in the first set, we are considering as 0 bar. In the second vector space, 0 bar also can be representing as like 0 cap or 0 tau. So kernel T is what? U belongs to V such that T of U equal to 0 bar, where 0 cap is a 0 vector in W. So kernel of linear transformation T is always subset of V and also a subspace of V, because when you are taking kernel T values, when we are where we are taking from first set or second set? Yes, obviously from first set we are taking, that's why it is a subspace of first vector space. Now range of a linear transformation means the set of all vectors in W of the form T of U for some U belongs to V is called range of a linear transformation. See, this is V and this is W. Suppose you are taking U, then T of U is belongs to range set. These total are belongs to the range of a linear transformation. So T of U, T of V, whatever they are giving. Suppose W, it is have image as 0 cap, then these all second set elements are nothing but range of a linear transformation. So range is subspace of obviously W. So range is a subset of W and it's also a subspace of W. Whereas kernel T is subspace of first set and range is subset of second set. Now kernel T intersection range T means they have no common vectors except 0 vector. Only the common vector in kernel T and range T is only 0 vector. Similarly, linearly independent set means we are taking some finite set of vectors, and when we can say this set is linearly independent in the sense we are taking a linear combination of these all vectors. How many vectors are given here? P. That much of scalars we should choose, C1 up to Cp. Take the linear combination equal to 0 bar. In this linear combination, suppose all the scalars are 0, then we can say it is linearly independent. Suppose in the same linear combination at least one scalar is non-zero, not all 0, that means at least one scalar is non-zero, then we can say it is linearly dependent. A set containing 0 vector is always linearly dependent, since when you are taking how we can say it is linearly dependent or independent? We can take the linear combination. Only one vector is given means one scalar we should choose and take the linear combination as CV or CV1 equal to 0 bar. In this V is 0 bar it is given means obviously it may not be 0. So C not equal to 0 means obviously it is linearly dependent. But whereas in a set containing single vector which is non-zero vector, then it is linearly independent, because when you are taking the linear combination when you are taking V is non-zero means 2 product is 0 means it is non-zero in the sense absolutely it is 0. So C is 0, not 0 bar. Here 0 is C is a scalar, that's why C equal to 0. Here only one scalar is given and all the scalars are zeros here, that's why it is linearly independent. And also obviously empty set is considered as linearly independent set, and a set of two vectors is linearly dependent if and only if one is a multiple of other. Suppose here you are taking v1 v2, v1 v2, one is the multiple of other, v2 equal to some c into v1. When you are taking into this side, what will happen? C v1 minus v2 equal to 0. This is the linear combination of vectors v1 and v2, where c may be 0, but here this coefficient is minus 1, which is non-zero. At least one is non-zero, then we can say it is linearly dependent. That's why one vector is the scalar multiple of other, then these vectors it is linearly dependent. So these are the basics for basis. And basis of a vector space means V is any vector space, and B, when you are taking a finite number of set, when we can say it is a basis of V, in the sense it should satisfy two conditions. One is V should be linearly independent set, and V equal to span of V1 to Vp. So B must be linearly independent set, and V can be expressed as linear combinations of all vectors of B. Then we can say B is the basis for vector space V. See one example. A is an invertible n cross n matrix of column A is a base of R power n because they are linearly independent of R power n, span A. So A is of n cross n matrix means it contains n columns, right? So n number of vectors are given with R power n means it is obviously span of A. That's why it is a basis of R power n. Similarly, E1 to En be an n cross n matrix which are the identity matrix like 1 0 0 0 1 0 like this. Then this is obviously a basis because it is obviously a linearly independent set and it is spanned by the vectors. That's why it is obviously a basis of R power n, which is called the standard basis of R power n. Say this, S is given, then prove that S is a basis of Pn. What are the conditions for basis? S should be linearly independent and it is spanned by the vector. So let us take Pn is a vector space with degree n, means it must contain n plus 1 vectors, isn't it? Because when you are taking as a polynomial with nth degree, up to this n numbers including constant, n plus 1 vectors should be there, right? So here also S contains n plus 1 vectors. This to this n vectors plus 1, n plus 1 elements. To prove it is a basis for Pn, take Pn, and Pn is obviously span of these vectors because Pn can be expressed as all the linear combination of these vectors, right? That's why Pn is span of these all vectors, because scalar into vector like this. It is a linear combination of all vectors. So Pn is spanned by S vector. So first condition proved. To prove it is linearly independent set, how many vectors it is given? N plus 1 vectors. So n plus 1 scalars we must choose. Then take the linear combination equal to 0 bar. Then 0 bar we can also write it as 0 plus 0t. Please, in terms of polynomial we are writing and comparing constants. Then a naught equal to 0. Compare t terms. Then a1 equal to 0. Compare t square terms. a2 equal to 0. Like this up to an equal to 0. Here we are taking n plus 1 scalars and all the scalars are 0. According to the definition of independent, it is linearly independent. It is linearly independent. So Pn equal to span of S and S is linearly independent. So S is the basis for Pn. So for linearly independent and dependent, we have another formula, simple formula. Suppose we are taking P vectors with P entries, means same number of rows and columns are there. Then we can take linearly independent. S is linearly independent when the determinant is not equal to 0. Linearly dependent when the determinant is equal to 0. That means same number of vectors with same entries are given. Then take the determinant. If it is not equal to 0, then linearly independent. Equal to 0 means linearly dependent. Let us see in problems. Determine whether the following vectors are basis of R3. So here 3 vectors are given, choosing as V1, V2, V3. Take as a set. Then R3, here it contains 3 entries. That's why R3 is a vector space here. To prove S is a basis for R3, it is enough to prove two conditions. One is span condition, that is to prove vector space R3 equal to span of these vectors. So obviously in this R3 means it must contain 3 entries and S contains 3 entries and 3 same vectors, same number of vectors are there. Obviously it spans. So it has 3 vectors with the exactly 3 entries. That's why R3 is span of V1, V2, V3. That is nothing but span of S. And to prove S is linearly independent, previously we discussed when 3 cross 3 matrix is given, then take the determinant of these 3 columns as vectors as columns here. Take the determinant 1 into corresponding row and column should be eliminated, and 1 minus 0. Alternatively, minus 1 into 0 minus 0. 1 into 0 minus 0. Then 1 will come which is not equal to 0. So, determinant is not equal to 0 means it is linearly independent. So, from these two what we can conclude, it is the basis for R3. Similarly, we can prove the next one also. V1, V2, V3 are given. And to prove R3 equal to span of S, S contains 3 vectors with exactly 3 entries, therefore it is spanned by S. And S is linearly independent means take the determinant 1 into corresponding row and column should be eliminated, and 0 minus 0 means 0. 0 into anything is 0, 0 into anything is 0, that's why it is 0. It is equal to 0 means it is dependent. It is dependent means it is not a basis for R3. Similarly, see this problem, same 3 with 3 entries, R3 is spanned by S. Then linearly independent means 1 into 1 plus 4, and minus 3 into corresponding row and column are eliminated, then 0 minus 3. Next minus 2 into 0 plus 3. Then after simplification you are getting 8 which is not equal to 0. It is linearly independent, so it is a basis of R3. Similarly, we can take V1, V2, V3. It is span of R3 equal to span of S because 3 vectors with 3 entries and S is linearly independent means take the determinant. The answer will be minus 34. So it is linearly independent. So it is a basis for R3. See here V1, V2 with 3 entries are given. 2 vectors with 3 entries. Determine the set V1, V2 is a basis of R3. So V1, V2 and R3 is a vector space, and to check it is a basis for R3, S contains how many vectors? Only through 2 vectors with 3 entries. So it do not span, obviously it do not span R3. That's why R3 is not equal to span of S. So no need to check for the next condition. Obviously it is not a basis for R3. See here, to check S is a basis for R2 means S contains how many vectors? 2 vectors of course. How many entries for each vector? 3. But it is belongs to R2 or not? No, because it contains 3 entries. So it does not belongs to R3. It does not belongs to R2. That's why obviously it is not a subset of R2. So no need to check for span and independence. Obviously it is not a basis for R2. See the next question. Vectors, 3 vectors are given, spans R2. It is already given that these 3 vectors span R2 but don't form a basis. Find 2 different ways to express this as a linear combination of 3 vectors. See, when you are observing here, not equal, vectors and entries are not equal means here not span, we discussed this one. But here, see, number of vectors are 3 and entries in each vectors are 2. So number of vectors are greater than that entries, then it spans that vector space. Clear? Here number of vectors are less than entries, that's why it do not span. Here number of vectors are 3 and entries are 2, that's why it is more than entries, that's why it spans R2, which is already given. But do not span, it is saying. Then see, R2 is a vector space. Take 3 vectors. Already given that R2 is spanned by these 3 vectors. And suppose it is asking that this vector is a linear combination of these 3 vectors. So this vector belongs to vector space. This can be expressed as linear combination of these 3 vectors in the sense. Take 3 scalars because 3 vectors are given. Take the linear combination which is equal to 1, 1. So 1, 1 equal to A1 into first vector, A2 into second vector, A3 into third vector. Now take the augmented matrix like first column, second column, third column and 1, 1. Now do row operations. How we will convert this into 0? R2 plus 3 into R1. R2 plus 3 R1 is 0. R2 plus 3 into means 6 minus 8 minus 2. 3 R1 means minus 9 plus 7 minus 2. 3 R1 3 plus 1 4 here. Again this whole divided by minus 2, then 1 minus 2 will come. Now converting into equations. A1 plus 2A2 minus 3A3 equal to 1 and A2 plus A3 equal to minus 2. Now A2 we are converting in terms of A3. And from equation 1, a1 equal to 1 minus 2a2 plus 3a3. Okay, so again substitute a2 equal to minus 2 minus a3, substitute in this, then you are getting a1 in terms of a3. So here a1 equal to in terms of a3, a2 in terms of a3. So here a3 is linearly independent vector, so scalar, independent scalar. Now when you are substituting a3 equal to any real number, suppose I am taking a3 equal to 1, then a1 equal to, when you are substituting 1, then a1 will be 10, a2 will be minus 3. Then a1 equal to 10, a2 equal to minus 3, a3 equal to 1, substitute in this, then you are getting one linear combination. Similarly, how many possibilities? Infinite number of possibilities are there. You can take any a3 value, then you are getting linear combination. Suppose I am taking a3 equal to 2, then a1, a2 we are getting some different numbers, then we are taking in this, then this can be expressed as linear combinations of these three vectors. We can representing in many ways, but it is asking in two ways it is asking, that's why we are finding two ways. In the next video, we will discuss about spanning set theorem.